Okay, and thank you, and good afternoon. So I'd like to talk to you about my thoughts about the foundation of the crypto economy. All these meetings are usually called blockchain, but very likely blockchain will be superseded by other structures such as a tree. So maybe it's not such an accurate description. So more general description could be called crypto economic science. Economic science, I think, has always been viewed as not so precise compared to natural science. But I think crypto economic science could be precise. And particularly in this talk, I will draw connections between natural sciences and crypto economic sciences. And hopefully we enter into a new era where the foundations of this new crypto economic science could be a lot more solid. And then we will be able to make more precise predictions. So these days we all talk about blockchain and crypto as a medium of exchange. So I first like to draw some analogies to help us to ask the question and possibly answer the question about what's the intrinsic value of a medium of exchange. So very early on I give an example, since I'm a theoretical physicist, I give an example in terms of physics. But hopefully this is an example all of you have learned in high school. When you have two charges, or when you have many charges, we describe their interaction first in terms of a pairwise interaction. Like charges repel and like charges attract. But the most remarkable thing is that they can interact with each other at a distance. And so we first exchange goods to money and then goods to other goods. So you see the analogy is very, very precise. Whether we describe pairwise interaction between charges, this is like barter economy, and then we describe the interaction between charges through a medium of exchange, which we call electric field. And in this case, in the monetary economy, we exchange things into a medium of exchange, which is money, and then we exchange money into something else. But then the question, we always view money with some suspicion, especially if we have paper money. And we always like to ask, what is the intrinsic value of money, especially if we're holding a piece of paper. And the same question has been asked in the world of science. What is the intrinsic value of this medium of exchange? Is this just a convenient way of bookkeeping, or does it have some kind of intrinsic value? Does the electric field have some intrinsic value? Actually, this question was asked but then answered by Albert Einstein. So in the very early on, it was just introduced as a matter of convenience. It's some bookkeeping device or mathematical construct. People didn't view it as having some physical reality. But Einstein changed that. You may all know Einstein is famous for special and general theory of relativity, but he did not receive Nobel Prize for either one of them. He actually received Nobel Prize exactly for assigning an intrinsic value to electric field, for the electromagnetic field, namely for effect, which is called the photoelectric effect. So electromagnetic field does have an intrinsic identity and also has an intrinsic value. Now, what would be the value in physical world, in the scientific world? The universal value in the physical world is energy. And Einstein's formula assigned energy to electromagnetic field. For example, the energy depends on the frequency. The blue light will have higher energy than green light, which will have higher energy than red light. So this is a revolutionary step. And it's a step in which we the concept that was introduced mere as convenience, as a bookkeeping device, but suddenly acquire intrinsic value of its own, and the intrinsic value can be very precisely defined through this formula. So now we come to monetary economy, and we ask, what is the intrinsic value of money? And I would like to argue the intrinsic value of money lies in its consensus. So let's compare two things. One case when we use Apple as a medium of exchange. Actually, I strongly suspect this may have been used early on in human society. Some goods, which both have commodity value, but may also be used as a medium of exchange. Now, if we contrast Apple as a medium of exchange with gold, why did we eventually adopt gold rather than Apple? Apple seems to be far more useful because besides a medium of exchange, Can I get some water? Yeah. Besides convenient medium of exchange, it could also have commodity value, namely I can eat it. So why don't we use apple as a medium of exchange? And that's because there's no consensus about what is meant by one apple. So one apple can be green apple, which will have a red apple. The red apple may have more value than a green apple. Its size may differ, and it also doesn't stay on, so its value tends to decay. So if I look at the apple, I first need to ask how many days has it been there, picked from the tree, and so on and so forth. So when we look at this curve, maybe under the concept of one apple, we don't quite agree, and the value we assign to one apple varies very broadly among the participants of economy. Especially if we broadly have three kinds of people: those that produce apple, those that consume apple, and those who simply use apple as a medium of exchange. And they have different ability to assess. Especially if I neither produce apple nor consume apple and simply use it as a medium of exchange, I don't exactly know how to assess the value, at least not as well as those who produce and those who consume. So therefore, when we use apple as a medium of exchange, its value is assessed very differently. In other words, there's no consensus about its value, and therefore it's inconvenient to use it as a medium of exchange. Now, why does gold have consensus value? And that's again because of two famous physicists. One is Archimedes, and the other is Isaac Newton. So you all know the famous story of Archimedes, the king of Syracuse, received a golden crown. He actually asked his handyman to fashion a golden crown for him, but he has the strong suspicion that the crown was not made out of pure gold. The handyman somehow substituted gold with some base metal, which is less valuable. So he gave Archimedes the task of figuring out whether the crown is made out of solid gold, actual pure gold, or some base metal has been mixed in without destroying the crown. So that was a very, very, very difficult task even for Archimedes at that time. So he got very depressed the last day when the king's task he has to answer. He knew that he just have to give up. He couldn't figure out. So he took a bath, just like in the Greco-Roman days. Whenever people need relaxation, they go to take a bath. And as he was floating in the bathtub, he suddenly had an idea, know how to measure whether the crown is made out of actual gold without destroying the crown. So you know, Isaac Newton was a famous physicist. He discovered the law of motion, law of gravity, and when he became famous, the Queen of England wanted to do him a favor to give him a higher paying job. So he became the master of the royal mint. His job is to fashion those golden coins. So he has to face this problem of debasing the golden coin, namely the kind of the loss of consensus of one golden coin because of this business that was going on. And it was he who invented this idea to put in these stripes around the edges of the golden coin, so that when you attempt to rub it, you immediately see the stripe has been destroyed. So this was another major contribution. So these are two great physicists, but they contributed greatly to the monetary economy. But the essence of their contribution is to give consensus to what is meant, either by 1 ounce of gold or by one golden coin. So if we really understand that the intrinsic value of money lies in its consensus, we may ask, why is consensus so valuable in the natural world, let's say? We can first ask this question. So anytime, I think maybe most of you, when you wake up early in the morning, you go to your refrigerator maybe to get a glass of milk. And usually people stick some magnets on their refrigerator. So how does this magnet work? Why does these magnets stick onto your refrigerator? So actually every material, so most material will not stick onto your refrigerator. Actually, every material is magnetic in some way because all materials are made out of electrons, and electrons act like a little magnetic compass. They have a north pole, they have a south pole, and they are magnetic. But in most materials, they are in a state of the extreme right. because we have many such magnets, but they all point in random directions. So they don't agree on a common direction to point to, and therefore they don't behave overall like one piece of single magnet. Something miraculous happens inside a magnet. It goes what is called a ferromagnetic ordering. All these electron spins, which act like a little magnet, suddenly, somehow, by communication and by interaction, reached a consensus. They all agree on one direction to point to. And that once they agree on one direction to point to, they have a macroscopic magnetization. So they act like a giant piece of magnet, and that is the reason why it sticks onto your refrigerator. So therefore, you see that in the natural world, without a centralized entity, somehow these random electrons can reach a consensus. They can agree on a uniform direction to point to. And that's a remarkable phenomenon. So why it is this state of uniform magnetization so hard to reach? Because there are few states of this kind. It's either they're all pointing down or they're all pointing up. There are only two such states. But there are many states where they can point in random directions. And all things being equal, it's much more likely to point in random directions than pointing to a uniform direction. So we say the state with uniform consensus is the state of low entropy. The state of high randomness is the state of high entropy. And the natural world, if you are left alone, always tend to increase entropy. The world always tend to become more and more random. And this is called the second law of thermodynamics. So that's why if you have a state of low entropy or you have a state of consensus, it's extremely valuable because it seems to counteract a natural force which always makes things more random. In fact, life is such a phenomenon. Life is a phenomenon we become very highly ordered, but our environment become more disordered. So I gave the example on the left, but this is really because before the blockchain and all this was invented, people find highly counterintuitive. How come without a centralized entity we can somehow reach consensus? But you can answer this question by not looking at the networking world. Even if you just look at the physical world or the biological world, you see that they can reach consensus without a centralized entity. I already gave you the example of the magnets. So somehow, naturally, they tend to be disordered. In fact, most material are non-magnetic. But somehow, they can reduce their own entropy by becoming more ordered, but by dumping entropy somewhere else. So this is the only way to do it. You can only reach a state of consensus if you somehow can dump entropy somewhere else. A similar phenomenon also happens in the biological world. These days in the blockchain world, one word that's used a lot is called a quorum. In the Byzantine fault-tolerant protocol, we also try to reach a quorum. Namely, we get people to agree or reaching a consensus. And in the biological world, there's also a phenomenon called quorum sensing. So if you have a lot of bacteria, and they can all emit some receptors. So if there are not so many bacteria around one particular bacteria, it does not receive that many receptors, and he knows he doesn't have that many neighbors. But when there are enough bacteria around, then he receives a lot of receptors, and if that reaches a given threshold, all of these bacteria will decide to lighten up. So this is called bacterial fissure. They suddenly in deep sea, when there are enough of them, they can all light up. And once they all light up, they can see, even in the deep sea, and they can find food for themselves. So this is another very interesting mechanism. But again, it happens in a self-organized way. It happens in an emergent way without a centralized entity. But they can only do so by dumping the entropy somewhere else. Now let's come to the networking world. So in the system of distributed computing, so computers are made out of atoms. So in some way, you can view this collection of distributed computers. They're not so different from a collection of electrons, a collection of bacteria. They all act in some independent way. And if they're left to themselves, they all behave somewhat randomly. They don't agree on things. But in a distributed system, it's very, very important to agree on something. One of the very important things to agree on is timing. So if we want to perform some synchronized task, they have to perform the task in some choreographed fashion. So then they have to communicate with each other. They have to agree on a global time. But how can they do that, especially if some of these computers can get hacked and if they can behave maliciously? Is there a way to have a centralized algorithm without much cost? It can direct all these computers to behave in some collective way, even knowing some of the computer can behave maliciously. So people tried and tried and tried, and they eventually found out that it is impossible. But usually, among us, if we try something and we find it impossible, we just give up. But mathematicians are smarter than that. They actually proved that this is not possible. So this is beyond what we usually do. Usually, we try enough times, we just give up. But mathematicians actually try to prove that try to save some work for the future generations. So they actually proved that a central deterministic master algorithm of this kind is not possible. And this is called the Fisher-Lynch-Patterson theorem, which says that without any cost, a centralized deterministic algorithm, there's no way to direct all of them to reach consensus. So this is very much like a phenomena or a concept we have introduced in physics, and that is called the concept of a Maxwell's demon. This is some entity, it's like a centralized entity, which can tell how each gas molecule is moving, and can somehow collect all the fast-moving molecules to the right and slow-moving molecules to the left, and thereby creating some ways to do work for a random gas. And we know another statement of the second law of thermodynamics is called perpetual mobilities are not possible. 永动机 is not possible. And this is the same as saying Maxwell demon is not possible, which is the same as saying Fisher-Lynch-Patterson's theorem says that a centralized master algorithm behaving in a deterministic fashion is not possible. So somehow there has to be a cost in reach consensus. And the remarkable thing of the blockchain world, this is why I find that at a fundamental level, this concept of proof of work in the Bitcoin blockchain is very fundamental invention. Basically, the thing we need to reach consensus about, so here the electron decide to point in the same direction. Here the bacteria decide to lighten up in exactly the same time. And here in the blockchain Bitcoin world, we try to agree on a ledger, and particularly on the timing of ledger. And we cannot do so without cost. So you have to have some cost. And here it is done by performing this hashing puzzle that you do have to waste electric energy, and in the process of doing so, you created extra entropy such that you can reach a state of lower entropy, namely agree on a ledger of transactions. So a lot of times the Bitcoin blockchain world has been criticized because it seems to be wasteful in wasting this energy in reach consensus. But actually it's fundamental. Just like you cannot get a heat engine to work without dumping some extra heat. You cannot perform a perpetual mobility. You cannot try to reach consensus without wasting any energy. Now, of course, this is a qualitative statement. Much more interesting piece of work could be try to assess quantitatively whether there's a lower bound on the energy that you have to waste in reaching this consensus. But overall, I think this is going in the right direction. So I think a lot of attempts try to do blockchain scaling. Some of them claim that they can achieve a much faster transaction without any waste. Don't believe any of those. This cannot be possible. Yeah. So now we use this way of viewing to look at the trends, overall trends in the networking world. And I summarize this as a cyclic evolution of centralization versus decentralization. So in Chinese, it's called 分久必合，合久必分. So let's remember in the era of the circuit switching technology, with this technology, the most natural, in order to reach efficiency, a monopolized, centralized entity is the most natural one. So AT&T emerged as a centralized monopoly. It controlled all the networking resources at the time. And when I came to the United States first, in the 80s, AT&T looked like such a giant that it would last for 1,000 years. But little did we know that even one small change in the networking protocol, namely going from circuit switching to packet switching, TCP/IP immediately disrupted this centralized monopoly. That in this world, there's no value for centralized monopoly, and networking resources immediately become decentralized. But then, as the networking content, as the content gets more and more spread over the network, it's become very, very hard to find information and to organize information. So therefore, centralized entities emerge again, such as Google and Facebook. And they basically use the content that all of us generate. Basically, they don't generate much content of their own. But they're just organizing and redirecting those contents. And so it's their processing bits in very much the same way. With the old monopoly, let's say, of Exxon. What is Exxon doing? Exxon is rearranging atoms, right? So you can get crude oil, you're rearranging the atom. Rearranging atom is basically chemistry, and you get refined oil out. And Google and Facebook basically access the raw data, raw content that all of us create. They just organize and present in some different way. And that is become a centralized monopoly. So then with the blockchain world, I think it leads to a drastic new wave of decentralization. And this one will be most impactful. And suddenly, it becomes a self-organized way for a platform to reach trust and reach consensus. And fundamentally, it's all based on mathematics. So this is why I call this new era the era of in math we trust. So we may ask ourselves, if consensus is the most valuable thing, the most natural question we can ask is, among all branches of human knowledge, in which branch do we have most consensus about? You see, economists fight all the time. Social scientists fight all the time. Physicists don't fight that much because we more or less agree. But even less is the fight among mathematicians. If somebody proved the theorem, he proved the theorem. There's nothing to argue about. So in the mathematical construct, such as the beautiful construct of the Platonic solids that you see on the left, that in the real world, we can fashion a cube, but that cube is never perfect. We cannot agree whether this cube is so precise that every corner is in exactly the right location. But a mathematical cube is perfect. The idealized cube is perfect. And there's perfect consensus about what is a mathematical cube, even though we don't quite agree on a physical cube that actually has been fashioned. So that's why among all branches of human knowledge, we have most consensus about mathematics. Therefore, it's most natural to base our consensus of economic transactions based on math. When we look at the natural world in its most fundamental level, we see the basic laws of nature are expressed in terms of beautiful mathematical equation. The equation you see on the right pretty much describes everything there is to the world as we know it. So math in some way is the language of God. So if we say in God we trust, we might as well say in math we trust. So what kind of maths become the centerpiece of the crypto economic science? So first of all, there are these beautiful maths of public key and private key based on elliptic curves. This is what makes a transaction possible, or signatures possible, authentications possible. The cryptographic hash function have this critical property of being a one-way function. It's very, very hard to compute, but very easy to verify. So the entire blockchain consensus protocol is based on this one-way nature of the cryptographic function. So these things, I think most of you heard about. But when you actually come out to think about a new idea on blockchain or crypto economics, many of you, a lot of the entrepreneurs get somewhat confused. So for example, I recently heard a pitch somebody want to use machine learning as a consensus algorithm, that you do some machine learning computation and you try to reach consensus this way. But I think it's actually not a good idea, because it does not have this one-way nature. Because machine learning is basically doing a gradient descent, and that's not a difficult computation to do. But even if you found, so it doesn't have this one-way nature, very difficult to compute, but very easy to verify. So in order to have this property of reaching consensus, it has to be very, very difficult for anyone to find the solution, but has to be very easy for anyone to verify the solution. But this is the beauty of the cryptographic hash function. It exactly has this one-way nature. There's a beautiful idea of zero-knowledge proof, and this, I believe, is a piece of mathematics which will enable a data marketplace to be possible. So basically, the idea is that all our data should belong to us, and the privacy should be perfectly preserved. But still, under the condition of privacy preservation, we can still do certain kind of computation. And this is the miracle of the zero-knowledge proof. A famous example, just to illustrate, is that suppose there's a puzzle, let's say the Sudoku game. It's very, very difficult to find this puzzle. It is a 9x9 grid. You have numbers 1 to 9, 1 to 9, none of them. And none of the column can repeat, none of the row can repeat, and none of the 3x3 square can repeat. So it's a very, very difficult puzzle to solve. But suppose two of us, I try to convince you that I have solved this puzzle, but I don't want to give you the solution. Maybe I still want you to try, and so on and so forth. So is it possible to convince you that I have solved the puzzle, but without revealing my solution? So I only want to give you one bit of information. Either I have solved it or I haven't solved it. But if I give you all the solution, then it contains so much more information. So the idea is to selectively leak information one bit at a time. So whether it's possible to just leak out one bit, namely the very fact that I have solved the puzzle without revealing to you the solution. And the answer is yes. It's remarkable, as remarkable as the possibility of the public and private key encryption, the fact that you can pass keys around and still make authentication possible. This zero-knowledge proof will be a central piece of mathematics in the future of the data economy. We have talked so much about big data, we have talked so much about AI, but we haven't talked about how to do privacy-preserving data computation. And this is one way to make it possible. Then there's this idea of differential privacy, that if I conduct a survey, maybe it's a very, very sensitive survey that each one of you may be quite concerned in giving out some private information. But there's a protocol that each one of you can add certain noise to the answer of your survey so that it becomes not individually identifiable, but in a collective ensemble, the noise will cancel out. So then I will still recover exactly the correct statistical property of ensemble. And that's, again, because of a asymmetry. Each individual care about their privacy, but if I'm conducting a statistical survey, I'm not interested in exactly what each individual answer is. So you can be free to add your noise to your data so that you preserve your privacy, but it doesn't change anything in the statistical property of the ensemble. So this is, again, a beautiful idea of differential privacy, and we're using such idea, for example, for genomics-based computation. There's the idea of formal verification. These days, smart contracts are very popular, but people just claim because a smart contract can be very, very complicated. And especially, people haven't really thought about because we say, wow, a smart contract is possible, a public ledger is possible, maybe the economy or finance will be fundamentally changed. But some transactions are really, really complicated. And if you're writing a smart contract, and we see there has been a lot of cases that a smart contract was not written in a proper way, like the DAO hack, and then it could have been hacked. So is there a way to verify whether a smart contract does what it's supposed to do? And that is, again, a beautiful piece of mathematics called formal verification. The idea actually descended from some very original mathematics from the time of Gödel and Turing, who tried to prove the completeness of mathematics. And this eventually became useful in formally verifying whether a smart contract does what it does. The last graph shows what is called a DAG, a directed acyclic graph. So the idea is that a blockchain has the protocol of the longest chain, but maybe this is not the most efficient way. The most efficient way could be this DAG graph that you can do a proper assignment, so that a lot of the hashing power in the blockchain world, only the longest chain wins, and temporary fork all get lost. But in the DAG world, they all get some credits. So therefore, it's much more difficult to hack in this system. So now let me talk about a wonderful new world of AI plus blockchain in symbiosis. So what currently you hear in the last few years about AI being such a promising technology, but it's not exactly delivering what it has promised. And the most difficult part about AI, we have a lot of computational power. We have the GPUs, we have the TPUs, we have the algorithm of machine learning based on neural networks. What machine learning and AI needs the most is data. And that has been very, very difficult to come by. Basically because individuals don't own the data, and there's very little incentive for people to give data. So in the blockchain plus AI world, in symbiosis, we can create a crypto economy in which the individuals own the data, and they can perform privacy-preserving computation based on the mathematical primitive I just presented. And in this world, there will be a lot more efficient. People actually get paid for providing data, paid in tokens. Tokens can appreciate, and then finally AI can work. So I also think in the crypto economic world, in the data economy, finally we can do social goods, the likes of which we have not seen before. So in the current economic world, we have injustice in the current economic world, and the injustices are mostly manifested in the discrimination of minorities. And that is a universal problem in all societies and all economies. But now let's imagine if this data economy and data marketplace really take place. And let's say the AI tries to learn and improve. And let's say the AI is already 90% accurate. And I want to go from 90% to 99% and going from 99% to 99.9%. What kind of data do I need the most? The kind of data I need the most is not yet another kind of data that I already have learned before. So the majority was already learned in the process of 90%. What I need the most are those corner cases that can help my accuracy to improve. And the corner cases are exactly those that differ from the regular cases. They are by definition the minorities. So therefore, and this can be precisely measured by a mathematical quantity called mutual entropy. So in this data economy, the minority will be valued the most. And finally, we can do social goods by turning ugly ducklings into beautiful swan. Why? Because ugly duckling is not ugly. It's simply different. And the difference is valued the most in the AI plus crypto world. AI can finally also help to check and to make kind of proper surveillance of the data of the smart contracts that are on the network. And a lot of the kind of the compliance in the blockchain world, I think, is not possible by humans, but it's possible by AI. So now let me tell you very briefly about DHVC, the fund that I have co-founded about 4 years ago. The basic idea is manifested in this logo. First, you see the triangle. The top of the tip of the pyramid is innovation, and based on two bases on education and research. So in Chinese, this will be called 采学研. And then, so I'm a professor at Stanford. I'm an active research scientist, both teaching and research at Stanford. So we like to invest into the students. We like to invest into the latest research. For example, in the blockchain world, we work very closely with Professor Dan Bonnet at Stanford. And then you see the two crosses, and these are the two bridges we try to build. One is the bridge between the frontier of science and technology with investment, and the other is the bridge between US and China, both of which are the central themes of this conference. So let me tell you very briefly about so we, 4 years ago, because of this fundamental thinking, So today you see a lot of volatilities in the cryptocurrency world, but actually we have deep confidence even starting from 4 years ago. I saw that blockchain and crypto economics is really one of the greatest innovation of our time. I think when you go from 50 years or 100 years from now into the future, but let's say in 100 years, when you look back into our present era, what is the greatest innovation of our time? I would certainly think it's internet, but blockchain is internet times 10 or something like that. It's really something that fundamentally give a new protocol for humanity to work closely together. So we try to invest into the commanding heights of entire crypto economy, all the way into base coins, exchanges, the application layers. For example, very early on, we invested in Brave, the BAT token, but also the data token, which is very successful. Here on the ID verification, for example, New Cipher can really enable these privacy-preserving computation. CETIC is exactly performing these privacy. It's trying to do formal verification of smart contracts. Shoucheng is trying to do identity management, and so on. And so maybe on the lower right corner, you see Ontology, which is a token project trying to enable the entire data economy. It's performing extremely well because it just was announced recently. So what are the futures of the blockchain? Certainly, I think there are interesting scaling solutions. And I really like the Lightning Network and the idea of the Radar Network. But in the implementation details, there are a lot to be improved. So we're investing into this direction. We also invested in sharding of the blockchain network. One very interesting idea, I think, is the tokenization of the network infrastructure. And one investment we made is in CETA, this token, which is trying to tokenize CDN, content delivery network. So when the blockchain was designed, this interblock time of 10 minutes basically relies on network latency. But right now, the networking protocol is not using the blockchain or Bitcoin network at all. So, but if you can add an incentive layer onto the networking layer, and these two layers can finally work in symbiosis with respect to each other, and finally, they can all improve each other tremendously. I talk about the privacy-preserving data marketplace. This, I think, is really exciting. It will fundamentally change every aspect. But the fundamental idea is that the ownership of the data has to go back to the individual. They shouldn't be owned by the centralized platforms. But only with privacy-preserving computation, such privacy-protected data becomes useful, and privacy protection becomes possible, and possibly it can do social good, as I explained before. Tokenized sharing economy and identity management, and so on and so forth. So I would love to talk to all of you. We're very interested in finding really innovative breakthrough ideas in this crypto space. So I think in 1680, Newton published his Principia, which gave you the mathematical framework or mathematical foundation of all of the natural sciences. And, but so far, social science and economic science have been lagging behind. Finally, with the advent of crypto economy, and with the crypto economy based on the simple slogan of "In math we trust," I think we finally reach a new era in humanity where we can really have a precise mathematical foundation of the crypto economic science, and that will serve leads a tremendous progress in economic science as math did for natural science. Thank you.